Right. So in the last class, we are talking about elementary functions. We discussed about exponential function, logarithmic function, and sine and cos we are going to discuss today. So when it comes to exponential function, we found that it is a very nice function. Why? Because it is continuous and differentiable everywhere. But when it comes to the logarithmic function, it's not that much nice, because logarithmic function is not differentiable everywhere. You can see a line where it is not going to be differentiable. Of course, you can see a line that is what the negative x-axis, where it is not, where the limit doesn't exist. It means it is not continuous. It means it is not differentiable on that line. Okay, so I'm talking about principal logarithmic function. So we observed that when you take log z, it is actually one to many, but one to many we don't feel it comfortable when you take one to many function, right? So if you want to discuss about continuity, differentiability and all, so first you make that as one to one. Okay, even many to one is also fine, but we shouldn't have one to many. So first let us make a cut on the domain so that it becomes one to one function, right? So we observed that that cut is nothing but principal argument. That is, you take an argument where z lies in between minus pi and plus pi. So that's what we call argument, principal argument of a complex number. So this is how it is defined, and we observed that this principal argument is not a continuous function on the negative x-axis. Why? Because when you come from the top, the argument value will move near to pi, whereas when you come from the down, then the argument value moves to negative pi. So those two are not equal. So you can say that the limit doesn't exist, therefore it is not continuous. That implies it is not differentiable. That implies it is not analytic. So whatever is true for argument of z, which is going to be true for logarithmic function, log z, principal logarithmic function, right? So I can clearly conclude that principal logarithmic function is not continuous on the negative x-axis, right? And some people, they may define logarithmic function in a different way, like this is what the principal argument or the principal logarithmic function where theta lies in between minus pi and pi. But some people, instead of taking the negative x-axis, they might start with any line. Let's say here, let's say the angle making with x-axis is alpha. Now they are going to make a cut at this line. So they'll define their logarithmic function this way: log z equal to this is ln of mod z plus I into argument of z, and they'll have some restriction on this argument of z. Argument of z should lie between alpha and alpha plus 2 pi. It means what they are doing is they are actually considering this part. Okay, so here actually you started with negative, from negative x-axis to here. This is how you are measuring it actually. Like when you start from minus pi, you will end up with pi. Similarly here, when you start with alpha, you will end up with alpha plus 2 pi. So if you take a function in this way, a logarithmic function this way, then I can say that it's not going to be differentiable on this line. Okay, if it is principal logarithmic function, yes, we are very sure it is not differentiable on the negative x-axis. But just for convenience, if you define it in another way, instead of taking principal logarithmic function, you're taking a function which is similar to it, but instead of starting with the negative x-axis, you're actually starting there, starting at some line which is making an angle alpha with x-axis. So in that case, I'll say that argument value will lie between alpha and alpha plus 2 pi, right? And these are what we call branch cuts. Branch cuts. It means you're actually cutting at that line so that this becomes a single valued function. And you know that that logarithmic function is not going to be analytic along the branch cut. Here, for a principal logarithmic function, the branch cut is along negative x-axis. Whereas the other function, what I have written here, for this, the branch cut is along this line, which is making an angle alpha with the x-axis. So now here you can talk about derivative of log z in this domain, like except that line, everywhere else you can talk about its derivative. So the log z derivative is going to be 1 by z, and similarly we saw the derivatives of e power z and z power n. Yeah, and then we define sine z and cos z, trigonometric functions. And you can observe one thing, that sine x, if you take it as a function over the real numbers, that is going to be bounded, and it is going to take the values between -1 and +1. But when you come to the complex plane, sine z, that's not going to be bounded. It is going to be unbounded. Of course, we can prove that that's going to be unbounded once if we define hyperbolic functions. But anyway, you can see some evidence here. We are able to find solutions of sine z equal to 2. It means this sine function is taking the value 2. It means there is some complex number such that sine z equal to 2. Similarly, not only just for 2, you start with any number, let's say 500. So you can find a complex number z such that sine z equal to 500. And we can clearly guarantee that z must involve a non-zero imaginary part. If it doesn't involve non-zero imaginary part, it means it never never go beyond 1, and it never comes down below -1. Okay. Yeah, and we are discussing about w equal to e power z, and I mean, sorry, this is continuation of sine z equal to 2, right? The next thing, yeah, I asked you to do this problem. Find all complex numbers such that cos z equal to 10. Did you do it? Right. So anyway, you try to do this problem in a similar way, like you write cos z equal to e power iz minus e power e power iz plus e power minus iz by 2, and you take it that is equal to some number, like we want that equal to 10. So you just try to solve that equation. You'll get a quadratic equation. From that you need to solve. Right. Now let us try to discuss about logarithmic function properties, principal logarithmic function properties. Okay, so here you know that log of a power m, that's equal to m into log a. When you see that as a real valued function, you learned it. Okay, similarly, when you take a logarithmic function, you can say log of z power k, that k, it may be a real or complex. So you can write it as k into log z, no issue, when you do not have any restriction. If you take a generalized log z function, it means if you take one to many function, then this property is true. But if you take a function from the branch cut, it means, let's say if you take a principal logarithmic function, this condition is not going to be true. Not always true. Maybe there are some points where that holds, but definitely you can find some k for which log of z power k is not equal to k into log z. Can you see why it is not going to happen? If it is a principal logarithmic function, we want this argument of z, we want this to lie between minus pi and pi only, right? Of course, it's not going to take plus minus pi. So minus pi is strictly less than, argument of z is less than pi. But the moment you multiply with the k, this argument may go beyond pi, or it may come below minus pi. So in that case, definitely here you'll have an expression whose argument lies between these two, whereas here you'll have an expression whose argument may go beyond it. Why? Because you're multiplying with k, right? So in that case, they may not be equal. Okay, let me show you one example. The example is this. Let me ask it as a question. Prove that principal logarithm of I power 3, which is not equal to 3 into log of I. So this is the question. Now first of all, let's write what is I. I in the Euler form, which is nothing but e power I pi by 2. I'm writing its principal value. So, and when it comes to I cube is nothing but e power I pi by 2, right, whole cube. So this is same as e power I 3 pi by 2. But if you see this 3 pi by 2, which is actually bigger than pi, but I need a value which is in between negative pi and pi. So what will it be? Okay, let me do one thing. Instead of writing it in this way, let me write I as e power I pi by 2 plus 2k pi, and you have power 3, and this one I can say this is e power I, what I have is 3 pi by 2 plus, it's okay, even 6 pi, when you multiply with it you'll get 6k pi. You can simply take 2k pi itself. Why? Because k can be any arbitrary integer, right? So now you can see that if I take k equal to 0, 3 pi by 2, it goes beyond pi. So, but if I take k equal to minus 1, then what happens? What I have is 3 pi by 2 minus 2 pi. So which is same as minus pi by 2. Yes, we know that minus pi by 2, which lies between negative pi and pi, right? So therefore, since it lies between these two, you can clearly say that it is a principal argument, right? Now let me rewrite this guy. So this one can be written as e power I minus pi by 2 plus 2k pi. Okay, so therefore, if you ask me what is a principal argument of I'll say which is pi by 2, whereas the principal argument of I cube, which is minus pi by 2, right? Now let's look at its logarithmic function. So now log of I. Okay, let me see here, you have 3 into log I, so let me write 3 into log I. So this is 3 times of, the definition of this is ln of absolute value of I, that is 1 plus I times argument of I, principal argument. So which is nothing but 3 times 0 plus I times the principal argument here is pi by 2. So when you multiply with it, you will get 3 pi by 2 into I. So this is what 3 times of log I. Now let me see what is log of I power 3. So which is ln of absolute value of this is 1 plus I times of argument of this, argument of I cube. So which is 0 plus I times, we already found the principal argument of I cube is nothing but minus pi by 2. So finally what I get here is minus pi by 2 into I. So we know that these two are not equal, therefore we can conclude that log of I cube is not equal to log of I, 3 into log I. Okay, so if you take just a logarithmic function, this condition may be true, like if you do not have any restriction on the argument. But the moment you keep a restriction on the argument, these equalities may not hold. Like log of a power m may not be equal to m into log a. Okay, now you can look at few more. Log of z1 into z2, which is same as log of z1 plus log of z2, when you do not have any restriction on argument. But if you have restriction on the argument, this is not always true. That is log of z1 into z2, which may not be same as log of z1 plus log of z2. Okay, so let me write it here. This need not be equal to log of z1 plus log of z2. Okay, but we can say one thing, they can be equal if real part of z1 and real part of z2 both are positive. So you can write a statement. So if real part of z1 is positive and real part of z2 that is also positive, then you can prove that the principal logarithm of z1 into z2, which is same as log z1 plus log z2. Okay, and I suggest you to go through few more properties of logarithmic function. You go to that book, Brown and Churchill, right? So you solve the exercise problems which were given there. Okay, so that you'll get more clarity on it. Yeah. Now let's do one thing. Let's come to trigonometric functions. That is so the trigonometric function here is sin z. We already defined it. That is sin z equal to e power iz minus e power minus iz by 2i, whereas cos z, that's equal to e power iz plus e power minus iz by 2. Okay. Now let me define hyperbolic functions as well. I hope you already know what is sin hy and cos hy, but let me write it here. So here if I have sin hz, this is how it is defined, e power z minus e power minus z by 2, and cos hz, we should not write it like this. We should write it like this: sin h, we treat this as a function of z. Similarly, cos h of z, this is equal to e power z plus e power minus z by 2. Now I'd like to see the relation between sin z and sin hz, because you see here you have i's, whereas whereas here you can see there is an I, oops, and here is I. Here you don't have I's, that's it. So now let me do one thing. Let me see what is sine of Iz. Can it be expressed in terms of sine Hz or not? Let me see that. So sine Iz, which is same as e power, you have I into Iz minus e power minus I into Iz by 2I. So we know I square is minus 1, so this is same as e power minus z minus e power z, because minus into minus plus, by 2I you get it. So now if you take minus common, minus 1 by I, let me take it out. So I am left with this e power z minus e power minus z by 2. So this is what exactly sine Hz. So therefore you can conclude that sine of Iz, which is same as minus 1 by I, which is actually I times this is sine Hz, which is not, so sine of Hz. As that, just a minute. Okay, so you can see that sine of Iz, which is same as sine H, I sine Hz, and similarly you can see what happens to cos of Iz. Cos of Iz, that will be same as cos Hz. Okay. Now let us try to express this sin z in terms of x and y as a function of u of x comma y and v of x comma y. So here let me write sin of z, which is nothing but sine of x plus iy, that's equal to, you know, sin a plus b formula, sin a cos b plus cos a sin b. So using that I can write it as sin x into cos of iy plus this is cos x into sine of iy. Now you know what is cos of iy, you can write that is same as cos y, so this cos hy, so this is sine x into, you have cos hy plus this is cos x into this sine iy can be written as I sine hy. So therefore finally this is what we get, sine x into cos of hy plus I times this is cos x into sine hy. Okay, so this is what sin z. So here you can see what is u of x comma y and v of x comma y when you express sin z as u plus iv. This is sin z, and similarly you can do it for cos z. But before going to it, let me see what is the absolute value of sin z. So the absolute value of sin z, which is nothing but square root of this expression, that is what sine square x into cos h square y plus, and this is cos square x into, you have sine h square y. Alright, and we know some identities related to sin x, cos x, and sin hx and cos hx. What are the identities? We know that sine square x plus cos square x equal to 1. This is one identity we know, and the other identity in terms of hyperbolic functions, that is cos h square x minus sin h square x, which is equal to 1. So therefore you can see that cos h square x is nothing but 1 plus sin h square x. So this is 1 plus sin h square x. Now let me replace this cos h square x with that. When I do that, so this will become, you have sin square x, and cos h square y can be replaced with 1 plus sin h square y, plus you have cos square x into sin h square y. Now you can do one thing, sin h square y is common here and as well as here, so you can take it out. So when you do that, okay, so just for simplicity, I'd like to take square on both sides. So mod sin z whole square, which equal to sin h square y, you can take it out. So here I have sin square x, plus there I have cos square x, and there is one more term, plus you have sin square x. So which is same as sin square x plus cos square x is 1. So now you will be left with this sin h square y plus sin square x. So this is what absolute value of sin z square. Now you can see that sin hy is an unbounded function. So which from this you can clearly see that sin z is also unbounded function. I mean, the absolute value of sin z, it can be bounded when y is 0, because when y is 0 you'll be left with only sin x. You know, sin x is bounded because x is a real number. So sin x, the maximum value is 1 and the minimum value is -1. So that's going to be bounded. But the presence of y, the presence of imaginary part, makes it unbounded. Okay. So similarly, you do one thing, you take this as a homework. You do the same process for cos z. Express cos z in this form, that is u plus iv, and you find what is the absolute value of cos z. So take it as a homework and do it. And then next, what we need to discuss is inverse trigonometric functions. Okay, and if you ask me whether this sin z, cos z, these are all differentiable or not, yes, we can say they are differentiable. You can directly prove from Cauchy-Riemann equations, like it satisfies Cauchy-Riemann equations, and the first order partial derivatives of u and v exist, and they are going to be continuous. So from in that way, using that sufficient condition, you can prove they are analytic. This function is analytic. Or the other way is, you can see the sin z as a combination of these exponential functions, and you know these exponential functions are analytic functions, therefore their combination is also going to be analytic. So in that way, you can clearly say that the sin z and cos z are going to be analytic functions everywhere. And similarly, you can talk about sin hz and cos hz. They are also analytic everywhere. And then next, let us talk about inverse trigonometric functions. It means, suppose if you have w equal to sin z, now you are looking for z. That is z, you would like to write it as sine inverse of w. But remember one thing, here if you want to invert a function, that should be 1 1 and on 2. So when you take directly sin z, that's not 1 1, that's not I mean, it's not going to be 1 1. Why? Because Sin z, you can say that is actually many to 1, like many elements will be mapped to 1. For example, we saw the pre-images of 2, that is sin z equal to 2, the solutions of sin z equal to 2. It has infinitely many solutions. This k, the presence of k, which gives us infinitely many solutions, right? But if you want to discuss about inverse, then you make a restriction here. So make a restriction so that it becomes 1 over and on 2. So all that you need to do is you need to have a restriction on the real part. Let's say this is the complex plane. This is the complex plane, and see, in general we know where this sine inverse x is defined. When you see that as a real valued function, that's defined between minus pi by 2 to pi by 2. Do you remember this? Right? So now here also what you can do is you can cut this complex plane into a strip like this, like minus pi by 2 to plus pi by 2. So you can cut it to a strip. So once if you cut it, yes, there it becomes 1 1 and on 2. But is it true? If I cut it here, is it going to become 1 1 and on 2? What is your answer? Okay, so try to think about it. So you try to find a domain where it is going to be 1 1 and on 2. Like you can fix both, like domain and as well as codomain. For example, if you take sin x, I'm talking about real valued function. Sin x, which is going to be 1 1 and on 2 between minus pi by 2 to pi by 2 plus pi by 2 to minus 1 to 1. Here we have a restriction, and as well as here also we have a restriction. Sorry, this one is what I have written here is range. This must be a range. So similarly, what can you say about sin z? Where is it going to be both 1 1 and on 2? So that you think about it. So on the other side, what you have is real numbers. Why? Because for every not just a real number, I hope you can take a complex number as well, not just a real number. You can start with any complex number here, and here you should think about the interval. But here I shouldn't say an interval. You must think about a set. So that sin z from D to C, it becomes both 1 1 and on 2. That you need to think about it. Okay. So take it as an exercise question. So the homework question, try to think about it. Okay, let's assume we found the domain where it is both 1 1 and on 2. And after it, I'm doing this. Okay, so let me assume that that's the domain D. So on this domain, I'm taking inverse of it. So here z equal to what you have is sine inverse of W. But what is my aim? I want to express this z as a function of W. Okay, here I wrote it, but I should know what is this sine inverse of z. Okay, to know this, let me do one thing. Let me rewrite this as sin z equal to W. But you know sin z can be written as e power iz minus e power minus iz by 2I equal to W. My aim is to solve z in terms of W. Okay. So to solve it, you can multiply with 2 and both sides. which is 2iw. Now we take it to the denominator and take LCM, then you'll get e power iz whole square minus 1 minus, let me bring it to the other side, okay? So this is 2iw into e power iz, which is equal to 0. Now you can do one thing, you can assume this one as some k. Since I use w, I don't want to take it. X is not better, y is not better. Let me take it as k, okay? So I'm taking k is also not good one. What should I take? Let me take some z like this. Let me assume this, I mean e power iz. Okay, e power iz I'm going to replace with it. So this square minus 2 times iw, this and minus 1 equal to 0. Now it is a quadratic equation, you know how to solve for roots. So therefore the root is equal to 2iw minus square root of b square, which is 4 into I square into w square minus 4ac, minus into minus plus 4ac by 2a. Now if you simplify this guy, here you have iw plus or minus 4 can be taken out, so you have 2. This I square will become minus 1, so this will be square root of 1 minus omega w square. That's it. This is what actually e power iz, because xi is nothing but e power iz, no? So e power iz equal to, what I have is iw minus plus or minus square root of 1 minus w square. Now therefore iz is nothing but ln of, like, log of this function, iw plus or minus square root of 1 minus omega square. Okay, so here we are getting two things, plus or minus. Which one should I take? Should I take plus or minus? So we will consider only the plus part. Okay. So think why. So now if we consider plus, here you'll have just one quantity. So now it is easy. So from this you can see what is z. That's what 1 by I times, you know how this logarithmic function can be written. So this is ln of its absolute value. Absolute value is nothing but w square plus 1 minus w square under root, right, and this plus I into argument of this number. So how do you write its argument? We can't write this argument unless you know what is this w and 1 minus w square. So we'll do one thing, we'll simply leave it here. So therefore I can conclude z is nothing but 1 by I into log of this function, that is iw plus square root of 1 minus w square. In other words, sine inverse of w, that's what z is nothing but sine inverse of w, which is minus I, because 1 by I is minus I, into log of iw plus square root of 1 minus w square. So this is what. Okay. Similarly, you do one thing. You think about what is cos inverse of W. So try to construct that function and write it. Okay. So this is all for today. I'll stop it here.